Hey guys, what's up and welcome back to the Rocket Hub. My name is Philip and today we are going to dive into the world of one of the weirdest yet simplest methods of rocket propulsion. As always, the video is broken up into multiple chapters and the YouTube playbar is also divided into them. With that said, let's take a look at the crazy world of solid rocket boosters. When I started watching rocket launches as a child, I noticed an obscurity that no one I knew could explain. Back then, the shuttle was still flying and a pretty familiar sight for my younger self. But one day I watched the launch of a Delta IV Heavy, and one thing about that launch really confused me. When the space shuttle soared toward the sky, it left behind a giant column of white smoke, always indicating where the shuttle currently was. It truly appeared like it was riding this plume. But the Delta IV Heavy behaves different. Its exhaust is clean, blue and orange, almost transparent. The only visible clouds generated by the launch are evaporating water clouds on the pad. And when I asked people I knew why the Delta IV Heavy didn't leave a trail of smoke behind, I never got a proper answer. Luckily, it is 2022 by now, and I have learned a lot about rocket propulsion, as you may have noticed if you're watching a channel for a long time now. The real reason why the shuttle and the Delta IV Heavy show such drastically different exhausts is because they don't use the same fuel. While the core stages of both vehicles are powered by hydrolox engines, meaning they burn liquid hydrogen and oxygen, the side boosters behave a whole lot different. On the Delta IV Heavy, the side boosters are almost identical to the core stage and use the same RS-68 hydrolox engines. The shuttle, on the other hand, has two massive white sticks on its sides, a pair of solid rocket boosters, or short SRBs. But apart from generating a different type of exhaust, SRBs are much weirder than many people think. So, how do SRBs work? Why do we use them? And what are the problems involving their use? As the name already suggests, solid rocket boosters don't use the typical liquid fuel of basically any other rocket engine. Instead, their propellant mixture is solid. Well, solid is also not quite fitting. The mixture used inside most SRBs typically has the consistency of a rubber-like paste able to be squeezed and stretched. But there are many options which fuels and oxidizers can be used. In fact, even gunpowder found inside a firework rocket can be a solid rocket propellant, but that isn't really used in professional rocketry. The most common propellant mixture is made up of ammonium perchlorate acting as the oxidizer, atomized metal powder, for example aluminum, as the fuel, a burn rate catalyst like iron oxides, and a binder which either consists of hydroxyl terminated polybutadiene or polybutadiene acrylic acid acrylonitrile prepolymer. And since these names are very much unpronounceable, they are abbreviated as either APCP-HTPB or APCP-PBAN. Why do chemists always choose the worst names for their stuff? Seriously. Anyway, these are the typical chemicals used in solid rocket boosters. But other than using a solid form of propellant, solid rocket motors are far more weird than just that bit. Actually, solid rocket motors don't even possess a proper engine. How's that possible? Well, because they're solid rocket motors. In a typical SRB, the fuel is located along the inner edge of the hull with a channel left open in the middle. Since the propellant is solid, consuming it from the bottom up to the top would be dangerous, since a solid propellant doesn't accumulate at the bottom of a tank but rather sticks to the hull and only falls down in chunks. Solid material just behaves different than liquids. Since burning a propellant from the bottom isn't an option, the combustion actually happens at the very top of the booster. In the very tip sits an igniter that starts the combustion, which then automatically continues downward until all the propellant is burned. The exhaust generated by the combustion flows down toward the nozzle at the bottom of the SRB. Yes, the bottom of the SRB may look like an engine, but in reality it's just a nozzle used to contain the exiting exhaust and increase thrust as well as ISP, not an entire engine. Since an SRB hasn't got the ability to actively regulate the amount of thrust it generates and therefore hasn't got any throttle authority, solid rocket motors can only be throttled up or down by altering the amount of burn rate catalyst inside. And since solid propellant burns inside the booster like a candle, there is also no way to put it out. Once lit, these things just burn. To control the flight path of an SRB-driven vehicle, there are effectively only two options. Either we try to gimbal the SRB's nozzle to create a form of thrust vector control, as the shuttle's boosters did, or we control the booster by firing RCS thrusters. These can either be separate secondary thruster systems or vents on the outside of the booster through which exhaust can escape sideways, something only possible for solid rocket motors. There also is another type of solid rocket motor called a hybrid engine, in which only one combustion component is solid. For example, the engine used in Virgin Galactic's suborbital spaceships has a solid fuel but uses nitrous oxide, a liquid, as its oxidizer. The liquid fuel is led through the combustion channel in the SRB and combusts as it hits the solid fuel, although the two substances aren't hypergolics. The only difference between a real SRB and a hybrid engine is that the use of liquid propellant enables both shutting down the booster and throttling the engine, since the flow rate of the liquid oxidizer can be controlled by a valve. That's a quick rundown on how solid rocket motors work and what they look like. Next up, it may be helpful to check out where they're actually used. Solid rocket motors are actually pretty common in rocketry. Depending on the definition used for solid rocket motors, they were the type of propulsion that actually started pretty much everything. Technically, gunpowder-fueled firework rockets are solid rocket motors, which makes the technology over 1,000 years old. The solid propellants used today emerged way later though, most originate from the 60s or 70s. Due to being able to be stored for years without any risk of an explosion, something liquid fuels can't really achieve, SRBs were initially used for intercontinental ballistic missiles or ICBMs, like the LGM Minuteman. Therefore, solid rocket motors first appeared on orbital rockets derived from missile technology and especially smaller vehicles. And that has one simple reason. The key metrics used to compare any rocket fuel are normally specific impulse, density, and storage temperature. Typical liquid propellants, like Kerolox or Hydrolox mixtures, achieve a really high specific impulse, which is unit measuring engine efficiency. But liquid fuels have two big disadvantages. Since they're liquid, the energy density isn't that great, and to keep a normally gaseous fuel like hydrogen in its liquid state, the tanks have to be under pressure and require extreme insulation to keep the hydrogen from boiling off. Solid propellants, on the other hand, have an almost catastrophic specific impulse of a maximum 242 seconds for a P-band APCP mixture. But since they are solid, their energy density is really high, and they can be stored at normal room temperatures, meaning they are a lot easier to handle. But what does that mean for the usage of SRBs on orbital vehicles? Well, solid rocket boosters are ideal for the first stage of any given rocket. The job of the first stage normally is lifting the vehicle off the pad and to accelerate it out of Earth's atmosphere. To do that, Efficiency isn't the key to everything, but rather the pure thrust output. And since solid propellant has a very high density, it is ideal for that job. And that is why most solid rocket motors used in orbital rockets are mounted either as the first stage or supporting boosters at liftoff. Sometimes upper stages are also, but that doesn't make too much sense due to their low efficiency. Probably the most famous rocket boosters of all are the massive P-band APCP 4-segmented SRBs on the Space Shuttle. They burned out after just 127 seconds, each having burned through about 500 tons of propellant. At sea level, their maximum thrust is a whopping 2,650 tons or 26,000 kilonewtons. Considering that the boosters have a liftoff weight of 590 tons each, that gives them a thrust-to-weight ratio of 2.25. That is beyond anything a liquid-fueled rocket could ever achieve. These boosters also had reusability features like a refurbishable hull and parachutes to ensure a soft water splashdown. The boosters also featured a set of 4 smaller SRBs at the top to move the boosters away from the shuttle after separation. Out of 270 launched SRBs, all but 4 were recovered, and the final mission of the shuttle used a pair of boosters that had already flown 59 times previously. However, they weren't really reusable since almost half the booster had to be replaced each and every mission. Also, a 5-segmented version of the same booster is currently powering NASA's Space Launch System the same way the shuttle got assisted by these massive SRBs. The 2 SRBs launched on the Artemis 1 missions actually are shuttle hardware, they just got upgraded and made bigger by 1 segment. This very same approach is often used by orbital rockets, including the Titan IV, the Ariane 5, India's GSLV, and many more. Many vehicles also feature multiple smaller boosters, such as the Delta II, which featured up to 9 boosters, or the Atlas V with a maximum of 5 asymmetrically mounted SRBs. There also are quite a few launch vehicles using entirely solid fuel stages, like Ariane Space's Vega and Vega C vehicles, the Minotaur, one of the dumbest looking launch vehicles ever designed, and the Ares 1, which stands in close competition for the same title. Another popular use case for SRBs are launch escape systems. The motors pushing or pulling crew modules away from the rest of the rocket in case of an emergency have to be ready at any time, given that the rocket could always experience failure. That means the propellant of a launch escape system has to be stored over long periods of time and be ready to fire within milliseconds. Of course, solid rocket motors are more than ideal for that task and are therefore used by most launch escape systems, like on NASA's Orion Q capsule, all past NASA Crew modules, Blue Origin's New Shepard, and many more. The only real alternative to solid propellant in launch escape systems are hypergolic fuels, such as used on the SpaceX Dragon, but as we all know, they are really nasty to handle since they are highly toxic. Due to the same characteristics, solid rocket propellant is also often used in suborbital rockets or even in amateur rocketry. Their simplicity, the easy handling, and lack of explosive potential makes the solid rocket motors ideal for these kind of tasks. As you can see, SRBs are basically everywhere and have taken on many shapes and sizes. But the latest generation of orbital launch vehicles seems to avoid using SRBs more and more and instead prefer liquid-fueled boosters and stages. And that has one simple reason. Until now, we have only touched on why SRBs are used and how they work. But what we haven't talked about is why we maybe shouldn't use them. solid rocket boosters are frequently used to enhance a rocket's thrust output on liftoff and have already launched astronauts into space in the past. But despite that, SRBs have some hidden flaws in their very design which may be impossible to fix. One of these flaws is directly connected to SRBs running on solid fuels in the first place. Since SRBs are effectively operating without a proper combustion chamber, lacking injectors, fuel regulation valves, or other systems that could regulate or cancel combustion in an SRB, there is no way to shut them down. Once running, they burn through their fuel until there is nothing left. That alone isn't too bad, but it could very well turn out to be fatal. Should there ever be a catastrophic malfunction on a crewed vehicle using SRBs like the Space Shuttle, there is no way to stop the SRBs from running. That leads to two serious threats to the crew of the vehicle. Should they manage to escape the failure in a launch escape system, the still accelerating and potentially out of control solid rocket boosters could collide with the crew module and kill everybody inside. We got an idea of what that might look like in the aftermath of the Challenger disaster in 1986. After the explosion of the external main tank and following disintegration of the orbiter, which, by the way, was actually caused by one of the SRBs, the two massive boosters just kept on going and spun around wildly since they were out of control. Eventually, they were destroyed by range control, but the little excursion following the breakup demonstrated just too well what could happen. Just imagine a little crew escape module somewhere along the debris. Not the best spot to be at with two massive SRBs flying around there. And although the rogue boosters didn't hit anything that day, the death of the 7 astronauts on board Challenger was at least somewhat caused by the fact the shuttle ran on SRBs. And no, I'm not talking about the O-ring failure that caused the entire accident. There's more. The two SRBs flying around out of control couldn't even hit anything since the shuttle didn't even have a crew escape system. And that is partially due to the orbiter being mounted on the side of the rocket, making the use of classic launch escape towers impossible. But even though this option wouldn't work, NASA originally planned to implement a different system on the shuttle to ensure crew safety: ejection seats. It may sound crazy, but good old ejection seats aren't even that bad of an idea when trying to escape a malfunctioning rocket, and they actually were mounted on Columbia, but got removed later on. Why, you may ask? Well, ejection seats require one thing to function properly. The engines of the vehicle have to be shut down, or the astronauts will just inject into the over 1000 degrees hot exhaust of the engines and die immediately. That's really not beneficial. But since the shuttle was powered by the two largest SRBs in existence at the time, there was no way to shut them down and cut the hot exhaust, meaning the ejection seats were nothing but useless. The fact that the shuttle didn't even have a launch escape system was mainly due to being powered on SRBs. So, solid rocket boosters can be an immense safety risk for crews launching on SRB-powered vehicles. However, they are still used on newer crew vehicles like NASA's SLS Orion system, mainly due to having a lower probability of failure, since they almost haven't got any moving parts. But crew safety isn't even everything that is substantially wrong with SRBs. At the beginning of the video, I mentioned the visible difference between the exhaust of a liquid-fueled rocket and a solid-fueled rocket. Every vehicle using solid rocket boosters or stages leaves behind a column of light gray smoke, whereas liquid-fueled rockets don't. The exhaust of liquid-fueled rockets is mostly clear, depending on the fuel used. The three main fuels used as of today, kerosene, hydrogen, and methane, all produce their individual exhaust composition. Rocket Propellant 1, or RP1, a highly refined kerosene, is made up of hydrocarbons and therefore produces mainly carbon dioxide and water vapor as its exhaust. But Since even RP1 doesn't fully burn, we also get some soot and a few trace gases like sulfuric compounds and carbon monoxide, but their amount is almost negligible. Hydrogen is undoubtedly the cleanest rocket fuel we have as an option, since it is burned in its elemental form. Liquid H2 burned together with oxygen to form water vapor, which is the only exhaust you'll get from a hydrogen-fueled rocket. Also, that makes the exhaust almost transparent, only a slight bluish glow can be seen. And at last there's methane, the latest addition to rocket fuels. Since it is, just like kerosene, a hydrocarbon, it also burns to carbon dioxide and water vapor. However, methane doesn't produce any soot and only tiny amount of trace gases when burned, since it is, unless using natural gas, way cleaner than RP1. Just to make that clear, any combustion happening inside Earth's atmosphere also creates some nitrogen oxides or NOx in the process, but that always happens to every single rocket engine based on combustion. And now we get to SRBs. Other than the liquid fuels we've just analyzed, solid propellant set free some very nasty stuff when burned. Once again, I've taken the Space Shuttle's P-band APCP propellant mixture with atomized aluminum fuel as our example, since it is the most used and also best explored one. The emissions created by burning P-band-APCP are aluminum oxide, soot, carbon dioxide, hydrogen chloride, nitrogen oxides, and some elemental hydrogen, along with many different trace gases. That is a lot of different emissions, and their names already tell they may not be the greatest for the environment. Well, even worse. The alumina and chlorides, which are the SRB's main emissions, are actually ozone-depleting substances. Not good at all. Every single time an SRB is launched, it punches a literal hole into the ozone layer. These holes may fill up again over time, and with a launch cadence similar to that of the shuttle, the ozone-depleting capabilities of SRBs don't cause too much damage. But in places like the Kennedy Space Center, regular launches of SRB-powered vehicles could very well become a serious environmental problem. And we aren't even going to touch on all the other environmental problems caused by SRB exhaust, like ammonia and chlorines falling to the ground and potentially getting into the groundwater and so on. As you can see, SRBs have some serious flaws related to their design that might be impossible to fix. Considering all these issues, is there even a real future for them? For the past decades, solid rocket motors were used really often, either as entire stages, side boosters, and mainly as strap-on boosters to give the rocket a little extra thrust and payload capacity. But if we look at the next generation of vehicles, that trend seems to stop. And that has one simple reason, and has not even got that much to do with the flaws we've just discovered. In the new age of private and governmental spaceflight programs coexisting and dozens of companies competing for launch contracts, one of the key features of future rockets is going to be reusability. SpaceX started this trend with the Falcon 9 and Heavy and will bring it to the next level with Starship. Rocket Lab is experimenting around with the Electron and will reuse their upcoming Neutron vehicle. Relativity Space plans to get the fully reusable Terran R online by 2024, and Blue Origin is planning what is essentially a scaled-up Falcon 9. And these are just the most important reusable rockets designs we have coming up. But notice what they all have in common? Right, they're not using SRBs at all. To reuse a rocket stage, mainly the first one, you have to bring it back to the ground without damaging it, or the reuse of that stage becomes economically unviable. But since SRBs can't adapt their thrust output and can neither be shut down nor reignited, propulsive deceleration and landing would require additional liquid-fueled thrusters. And then you could just redesign the entire vehicle to be liquid-fueled. Yes, guiding rocket stages back to Earth using just aerodynamic braking and parachutes is possible, but the resulting splashdown in the ocean severely damages the hull and requires extensive repairs, as seen with the shuttle side boosters. A parachute recovery only works for smaller vehicles, following the Rocket Lab approach of catching the stages out of mid-air. However, the far more problematic part of reusing SRBs is the refueling process for the next mission. To refill propellant inside a rocket motor, the entire thing has to be disassembled and the propellant distributed inside. That's quite a complicated procedure, costing lots of time and therefore money. Therefore, there are effectively only two places where SRBs may survive. Since private companies are forced to evolve by competition and will likely almost certainly go reusable sooner or later, the only thing remaining are governmental space programs or companies launching mainly governmental payloads. And that distribution already starts today. Of all current and upcoming launch vehicles featuring SRBs, most are made by space agencies and are, of course, expendable. These vehicles include the Vega C by ESA and Arianespace, the upcoming Ariane 6, and of course the Space Launch System. But the future of these vehicles is, of course, more than uncertain. The only vehicle not developed by some space agency using SRBs that I know of is the ULA Vulcan, which uses strap-on boosters similar to the Atlas V. Seeing that even Western space agencies are starting to maybe move away from SRBs in the future, the only ones to still use them are probably going to be the space programs of countries with space programs not as far as the American, like the ones of Japan, India, or many smaller countries. Other than in small numbers and on missiles, SRBs will probably slowly vanish. Over the course of this video, we have learned a lot about how SRBs work, where we use them, and why we maybe shouldn't use them anymore. But should we? Well, in my opinion, yes. Solid rocket boosters are among the most primitive forms of rocket propulsion, yet they do provide a few benefits for anyone using them. In terms of sheer power and thrust-to-weight ratio, SRBs are basically unbeatable. But their simplistic design also makes them a problem that forces other parts of the vehicle to compromise, and in case of the shuttle, they actually made the vehicle less safe. And the environmental consequences of launching SRBs are just awful. Despite only being released in relatively small amounts, we shouldn't be blowing thousands of tons of ozone depletants into our atmosphere, or we may bring back good old ozone holes. That stuff is just way too toxic to exist in the 21st century alongside sustainable fuels and electric cars. But the thing that will deal the killing blow to SRB technology in the end are probably going to be advancements in liquid-fueled engine technology, like the high-performing RS-25 and Raptor engines. To develop a reusable and a both environmentally and economically sustainable rocket, liquid fuels have to be used. Ditching SRBs gives us more control over our vehicles and flights, more safety for our crews in case of failure, and does the ozone layer a little favor. Therefore, I believe that solid rocket boosters and their problems are, in fact, unfixable, and we should as soon as possible get rid of them, at least in orbital rocketry. And that's it on this SRB rundown. Let me know in the comments what do you think about SRBs, and if you enjoyed the video, which I really hope you did, why don't you hit the like button and subscribe to the Rocket Shop. I really appreciate your support. We see ourselves in the next video, and until then, I'm out. Cheers!